Okay, so today we will have the defense of Simon Mauras in front of the jury, where today we have in the jury Claire Mathieu from IRIF, who is a thesis advisor, Hugo Gimbert, who is at distance and who is a co-advisor. We have Amos Fiat from Tel Aviv University, who is a referee. Olivier Tercieux, who is professor at Paris School of Economics, who is the other referee. And then we have three examiners which are present. Michael Feldman, who is at a distance. Nicole Imolika cannot be here at the moment. There is Stéphane Thomasé, who from ENS Lyon, which is here, and I am Tristan Tomala, and I'm the president of the committee today. Okay, so we will start. Simon Mauras, you will present us your thesis, and you have 45 minutes.
Okay, great. Thank you all for being here. Today I'm going to tell you what I did during my 3 years, a bit more of PhD. And so my thesis is entitled The Analysis of Random Model for Stable Matchings. And I'm going to try and first explain you the title using an example. So the example is as a college admission procedure in a rather special college. So we have students on the left that have to be assigned to schools using a procedure in the middle. And the part analysis of my title is because we want to understand how this assignment is made. So the hat is an algorithm. And the first question we might ask is who gets what from this algorithm? And because it's an algorithm which interacts with agents, and those agents can be strategic, that means that students are going to report their preferences, schools are going to report their preferences, but they might want to try and lie to get something better out of the algorithm. And so a second question we might try to answer is who can manipulate in such setting? And so this example might seem a bit silly, but actually there is a lot of places where such market occurs. And I listed a few examples here. So the list is non-exhaustive, of course. But in the US, we have the assignment of physicians to hospitals and also of students to public schools. And so in France, the example that I found was where the AFANET procedure, which match middle school students to high schools, APB replaced now by Parcoursup, which matches high school students to universities, and SCEI, it's a procedure which matches class préparatoire students to grandes écoles. And I learned yesterday that there is a new procedure called the Trouve Mon Master, which might be a way to match bachelor students to master degrees. And so those are examples of matching markets. And let me go back to the example to give you an idea of what kind of problem we're trying to solve here. So the students on the left have preferences over the schools. So they have ordered preference list. And the schools have ordered preference list over the students. And some pairs might be unacceptable, which means that a student does not want to go in a school. And for the sake of this presentation, I'm going just to rename students and schools by letters and numbers. And because we're interested in what happens in real markets, we're going to look at random models. So random models are a way to model what happens in real markets. And we're going to assume that preference lists are drawn from some distribution. So when A orders his acceptable partners, he will use a distribution. And so to give you more idea on what I mean by distribution, here are two examples. So the first one is called popularity preferences. So imagine we have three students, A, B, and C, and each student is going to get a positive popularity. So A has popularity 8, B has popularity 4, C has popularity 1. And to build a preference list, to draw a preference list from this distribution, we're going to first draw the first student with probability proportional to the popularity. So that's going to be, for example, B with a probability which is 4 over 1 plus 4 plus 8. And then we're going to do this without replacement and build the whole preference list. So the probability of getting this preference list here, BAC, is going to be this product of fractions here. So that's a first model. A second model we can consider is the utility preferences class of distributions. And it comes from the following observation. Schools might sort students by grade. And they will rank the highest grade first, and then the second highest grade. And if I draw the grade from some continuous distribution for which I've drawn the probability density function here, we get another distribution over the preference list over the students. And so I've chosen those two examples so that in this they are equivalent, but we can have some more general distributions. So that's the motivation. So remember, random models are here to model the fact that we are looking at real markets. And now let me move on to the stable matching part of the title. So still, this is the instance, the problem we want to solve with preference list. And we might ask if this is a good matching or not. And the answer of this question is no, it's not a good matching. Why? Because we have a student here, B, who's matched with no school. And we have a school 2 who prefer B to the student it got, which is C. And 2 and B form what we call the blocking pair, and they want to leave the market and just ignore the solution of the algorithm and do what they just leave the market. And so we want to avoid blocking pairs, and a matching without a blocking pair is going to be a stable matching. That's the definition. So this was defined by Gale and Shapley in 1962. And I've drawn one example of stable matching on the slide. But actually, there could be a lot of stable matchings. So here is another stable matching, which is much better for the students. Look, all the students have their first choice, and all the schools have their last or second to last choice. And this student optimal stable matching can be computed using a procedure which is called the student proposing deferred acceptance procedure that I'm going to describe later. And there is symmetrically another matching which is optimal for the school, and this matching can be computed with the school proposing deferred acceptance. So to conclude this introduction, I'm going to make an execution of the deferred acceptance algorithm on preference lists that have been drawn uniformly at random. And you can see, for example, the school proposing deferred acceptance algorithm. I'm going to choose a school one at a time. They're going to propose. So in yellow, it's a proposal from a school to a student. And students keep the best offer they receive, and they reject bad offers, that's the red, and they accept green offers. And if I run the student proposing deferred acceptance algorithm, it's the same but symmetrical, with the student proposing to the schools, and the school answering those offers by keeping the best proposal each time. And so in this thesis, we're going to try and look at procedure to compute stable matchings on random models. And we're going to look at the difference between the school DA and the student DA procedures. So this is the map of the presentation of today. And at the center of my thesis is this goal of answering practical questions. So I want to answer questions that occur in real markets, and such as which procedure should we use? So should we choose the student or the school proposing deferred acceptance? That's a question. And in the first part of this presentation, I'm going to claim that both procedures are in fact equivalent if we look at the outcomes. And in the second part, I'm going to, or part 3, let's say, we're going to look at other questions that might occur. Feasibility constraint, like in school choice, for example, we don't want all the students to rank all the schools, so we might limit the number of applications a student can send. And this creates some things. We're going to look at it last. So first, I'm going to start with part 1 and part 2, and I claim that student and school DA are roughly equivalent. And so in this first part, which is based on results published in this paper, in EC20, I'm going to try and answer the following question. So you have students on the left still, school on the right. You know edges, which mean that students applied in these schools. And you know that the preference list of agents are drawn uniformly at random for now. And you really like this matching mu as a decision maker. And you might want to try and maximize the probability of this matching being chosen. And you have the choice between running school DA or student DA. And the question is there something you can do to maximize the probability of mu being chosen? So remember, the input is random, the algorithms are deterministic, so the output is going to be random. And so the first remark we can make here is that if we had a complete graph, then because it's uniform, all the matchings would be equiprobable. That's 1 over n factorial, and this theorem will be trivial. But the fact that the graph is not complete and there is a lot of asymmetry here makes this statement non-trivial. And so the answer of this question is that actually the two algorithms have the exact same distribution. And for this theorem, the rest of this part, I'm going to first describe the lattice of stable matching, which is going to be useful in the proof. And then I'm going to give you some ideas on how the proof goes. Okay, back to our example. So remember, we have students' preferences, school preferences that have been drawn from a distribution. So here's a uniform distribution. And we said that there is a lot of stable matchings. And those stable matchings, in fact, they have a nice structure. So if I look at all the stable matchings in this instance, it creates what it's called a complete lattice, where it's a partial order with an extremal element here with all the students getting their first choice or the best stable partner. The other extremal point is this matching with all the students or the schools getting their best stable partner. And in the middle, we might have other stable matchings. And I've drawn some edges between matchings when we have 2 consecutive matchings in the lattice. And I'm going to read this relation, it's a covering relation. So mu being on the right of this matching nu will be read mu covers nu. And so this result is due to Knuth and Conway in a book from 1976. So that's a classical result. And now we're going to use it for the proof of our theorem, which says that the output distribution of both procedures are going to be the same. So to compute the output distribution of a procedure, we start by fixing a matching mu and computing the probability of outputting this matching mu. So we said that school DA outputs a matching which is stable and optimal for the schools. And so it's going to, the probability of this is going to be the probability of mu being stable minus the probability of the matching being stable but not school optimal. And now we can use what we said in the previous slide with the lattice of stable matching. Not being school optimal means that there is another matching nu which covers mu. And this probability is the probability of a union of events. And probability of union can be rewritten with an inclusion-exclusion principle. And that's this alternating sum that I've written here. So that's for the school deferred acceptance procedure. And similarly, for the student DA, we can write the same formula. But if we compare the 2 formula, you see that those 2 terms are equal. But then we have very similar terms that only differs by the fact that mu is before or after nu in the. And to show that those 2 are equal, we're just going to show term by term equality in those two formula. And to show term-by-term equality, we can use a lemma. We can compute this probability. And it turns out that we can compute the probability with some integral formula. So those integral formula are due to Pitel in 1992. And this is a formula for the probability of mu being stable. And there are a bunch of other formula to compute the probability of everything we need. And here, the probability of mu covering mu1 is going to be equal to the probability of mu1 covering mu. So I'm going to go through the other formulas. And we show that it actually suffices to conclude the proof because we have term-by-term equality. So the probability of outputting mu is going to be the same. And so the two distributions are identical. And the corollary of the proof, if we want to go further and look at the actual probability of outputting mu, it's more of a fun fact than a theorem, but we can in fact factor this inclusion-exclusion principle formula with a sum of alternative terms, and those are products. So there is a determinant appearing here in the formula. So I won't bother you with the details, but that's a way to compute the probability. So this is the end of the first part. So remember, we said that the two procedures have the exact same output distribution. And let me move on to the second part, where I still claim that the student DA and school DA are roughly equivalent. But here I'm going to say that their outputs in some setting exactly the same matching. So this is based on results published in FCT this year. But before going to the results, remember I asked at the beginning this question that was, who can manipulate? So we have students and preference list, and one student, let's say IA, can decide to lie and try to get something better out of the algorithm. So A here could decide to just say that he does not want to go to school 2 and just wants to go to school 1. So that changes the instance. We have new stable matchings. And let's look at those new stable matchings. In fact, doing so, he eliminated those stable matching on the right that are more optimal for schools. So that's an example of successful manipulation. By truncating the preference list, you can get something better. And so this result is due to Dobbins, Friedman, Roth, Gale, and Sotomayor. And the main idea is that someone can always manipulate to get his or her best stable partner. So if you truncate your list, you can always ensure that you have your best stable partner if the algorithm does not give you this best stable partner. And so our theorem says that under some condition, the difference of rank between someone's best and worst stable partner is going to be a constant. And that means that by manipulating, you don't win much. You only advance like a constant in your preference list. And so that's not really worth it. And the incentives to manipulate, to misreport their preference list, is going to be limited. And the setting in which this is going to be true, it's going to be true when students have strongly correlated preferences. Strongly correlated means that most students are going to have roughly the same preference list, but not quite. And one way to have a model which has this property is the popularity preferences model that we discussed at the beginning, where remember we draw the schools one at a time with probability proportional to the popularity. So if the popularity of school I is 2 to the minus I, school 1 has popularity half, school 2 popularity a quarter, etc. And preference lists are going to look like this. So here are 10 examples of preference lists drawn from this distribution. And we see that they look a lot the same, but they're not quite identical. And so now we're going to go and see some sketch of proof for this theorem here, which says that all the stable matchings, or the best and worst stable partners of each person, are not too far away. To do so, we're going to first run the school default acceptance procedure. And we're going to relabel students such that school 1, the most popular school, is matched with student A. So I relabeled the student. So A is matched with 1, B is matched with 2, etc. And we're going to look at what other stable matchings there could be. So remember, it's the school default acceptance I used. So it's the school optimal stable matching that is on the slide here. And so other stable matchings must be better for the students. So here, I've drawn all the edges that students prefer to this matching here. And so look at the example of student A. Because student A is matched with some very popular school, it's unlikely that he likes some other school best. And so here in this example, A only prefers 2 to 1. And so there is a lot of edges. And if we look a bit deeper in this picture, we can see that there is, in fact, some structure. And the structure is induced by what we define to be as separators. And a separator is those red lines that I've drawn on the slide. And a separator has the property that no student above the separator prefers a school which is below the separator. So we have no edges crossing in this direction. And what does it mean is that all the students above the separator are quite happy with their school above the separator. And so we will not see any stable matching those students with those schools on the bottom. And by a pigeonhole principle, it means that student and school above the separator are going to be matched together. And inductively, the second separator, they will be matched together, etc. So that's how we prove that most stable matchings look the same. And now we need some kind of stochastic analysis of this property. We want to show that there is plenty of separators. And to decide if there is a separator, it's a property. And we're going to, the fact that there is a separator here might be not independent from the fact that there is a separator here. So the analysis needs to take care of conditional probabilities. And what we do is that we have a process which places separators. We're going to have a stochastic analysis of this process. In this process, students and schools are going to draw the preference list online. And so this stochastic process that we analyze, we can dominate it with a stochastic domination. And at the end, using Wald's equation, we can bound the size of tiers between two separators. So that's the rough idea of how the proof of this theorem goes. And that's what I wanted to say for this second part. So going back to the theorem, if preferences are strongly correlated, stable matchings, the best and worst stable matching for students look a lot the same because they have roughly the same rank. Part 3. So in the first two parts, we said that student and school default acceptance are roughly equivalent. But we didn't look at other questions, and that's a third question. So when we want to assign students to school, for example, in France, high school students to universities, it's not practical to have all the students ranking all the schools. We want to have like an upper bound on the number of applications a student can send. Otherwise, it will be infeasible to rank all the students. And so this might create some incentives because a student cannot really tell the truth. Telling the truth would be applying to the best 10 schools of France, but there is a high chance of being rejected from those best 10 schools. So when a student submits a preference list, he needs to be strategic. And that's what we're going to talk about in this third part. So let's see this question on an example. So once again, student on the left, school on the right. And let's imagine that I'm this student at the bottom. And I know that I have a grade of 3 out of 10. And I know that schools rank students by decreasing grade. And I know that the grade of the other students are drawn uniformly, are integers. I know that all the students, when a student goes to a school, she or he gets some value. And if I go to school 1, I get a value of 1. If I go to school 2, I get a value of 2, etc. If I go to school 4, I get a value of 4. And the question that I want to ask is, being a student who has a grade of 3 out of 10, what's the best strategy for me? In which school should I apply if I'm only allowed to apply to one school? And so to answer this question, there is a simple trick that we can use, which is backward induction. So having a grade of 3 it might be a bit complicated right now. Let's see what happens if I have a grade of 10 out of 10. So if I have a grade of 10 out of 10, basically all the schools want me, and no matter what I choose, I'm going to be accepted. So I can just choose the best school, school 4, and I will get a value of 4. But now if I'm a student of value 9, I know that student of value 10 apply to school 4. So I can compute the probability that there is a student of grade 10 that will give me the probability of me getting accepted to school 4, 3, 2, 1. And if I compute the maximum expected value I can get from schools, here as a student of grade 9, the best to do is to apply to school 3 and get a value of 3. So we do this inductively, starting from the end. So student of grade 8, etc. And when we arrive to a student of grade 3, we can see that the best this student can do, assuming that all the other players that have higher grade play optimally, is to apply to school 3, in which I'm going to be accepted with probability a third, and that will give me a probability, a value of 1, a payoff of 1. So that's a nice example, but it's a bit, it's only an example. And we're going to see how to generalize this to some extent. So to generalize this, we're going to use what is called Bayesian games. So Bayesian games deal with situations where players have incomplete information. So they know about themselves, but they don't know about the other players. And so to model this, each student's I is going to have a type called Ti, and Ti is going to be drawn from a distribution mu. And this distribution mu is known to all the other players, or all the players. And schools are going to sort students by decreasing score, and the score can be computed from the type of a student. So this is a game, and the strategy for a student is just a function which maps the type of the student to the preference list he needs to submit. So in case of just one application, it's just one school, but if I'm allowed 2 applications, a preference list would be a couple of 2 schools, etc. And so an equilibrium strategy would be a strategy for which no student has a best response than the strategy itself. So it's a solution concept usually used in game theory. And the theorem that we can have is an existence theorem, which proves that there exists at least one symmetric equilibrium strategy. Symmetric means that all the students are going to use the same strategy. And to prove this, we can use some well-known fixed point theorem. So all these types of game have been studied in particular by Milgrom and Weber. And they prove that for these classes of game, we have always an equilibrium. And the proof uses this Kakutani-Glicksberg-Fan fixed point theorem. So it's a complicated fixed point theorem because the set of types might be continuous, infinite. And so the set of strategies will be like an infinite dimension vector space, and finding a fixed point in such vector space is sometimes difficult. So that's for the existence theorem. And so this allows us more freedom on modeling situations. And I'm going to go on one example here. So here, assume that the types of students are going to be their math grade on the x-axis and the art grade on the y-axis. So student A here has a very good art grade, but a very bad math grade. And we have two schools, school 1 and school 2. School 1 is going to be a math school, and they're going to rank students with a weighted average of their grade, but putting more weight on the math grade. And the art school is going to be a weighted average, but putting more weight on the art grade. And so weighted average here can be represented. It's a fancy way of representing it. It's just a scalar product between vectors. And so in this game, I need to set a distribution over the set of types. And once I have this distribution, I can try to compute equilibrium. And so we can compute equilibrium for this game using a similar strategy than the one I described earlier with the backward induction. And that's what's on this slide. So in this slide, let's look at the first at the left picture here. Every point is a possible type. And I have 3 students, and each student draw a type uniformly at random from this set of points. And I've colored the point with the school in which a student of this type must apply. And so we see that when we increase the number of possible types, here it's 1,000, here is 10,000 possible points, it looks like it converges towards some nice figure. And so this will be the subject of the last theorem of this presentation, which is a convergence theorem. So if we assume that we have a sequence of distributions, so here it's mu1, mu3, mu1, mu2, mu3, and for each distribution, we computed an equilibrium. And if the distribution converges towards a distribution mu, so here the distribution I've chosen weakly converge towards the uniform distribution over the square. And if the sequence of strategies converges toward a strategy, here it looks like it converged towards a strategy P with a small spiration here, then under some extra continuity hypotheses that are satisfied on my example, then the strategy P, the limit, will be an equilibrium of the game. And the proof goes by contradiction. So remember, an equilibrium is a strategy for which there is no best response than the strategy itself. And so assuming it's not an equilibrium, it means that there is a best response. And the best response at the limit will also be a best response somewhere in the sequence of strategies. So in this part, we define a game, which is a Bayesian game. We show that on some types of examples, we can solve this game when the set of types is discrete, when there is some other structure. And when we have the number of possible types going to infinity, we can approximate equilibrium with a continuous set of types. So I'm going back to this map slide to show you where we went. So my thesis was centered around this question of answering practical questions. So which procedure to use? Are there some other feasibility constraints, like the limited number of applications? And those 3 parts are in fact 3 chapters of my thesis. And I've done some other stuff that I'm not going to talk about today, but just really quickly. In this chapter 5, I talked about the number of stable pairs, which is roughly a way of counting how many stable matchings there is. It's a different measure. In chapter 8, I've been interested in approximating the distribution in output of student and school DA. So if I want to compute, for example, the probability that a student is matched with the school. So chapter 8 contains conjectures about how to compute this probability. And in chapter 9, I look at the convergence speed of online deferred acceptance procedure, where, for example, in France, in high school, in Parcoursup, schools send proposals all at the same time. You don't have one school proposing then the other one, etc. You have all the schools proposing at the same time, and the speed of this process is crucial because you want it to terminate quickly. So here I have a small animation of school proposing all at the same time. And so that's it for what I did during my PhD. And let me try to show you a bigger picture on this last slide. So my thesis was about the analysis of random model for stable matchings. So stable matchings is one way to solve this problem of matching under preferences. Matching under preferences if you want to match students with schools, for example, but stable matching is not the only way of doing this. There is other procedure. And more generally, this problem belongs to to a more general domain. So computational social choice problems deal with problems where we're interested in the preferences of agents. And more generally, algorithmic game theory is the field I look forward to work in the future. That's all for me. Thank you for listening, and I will be happy to answer questions.
Okay, thank you very much. So we'll have now questions from the jury. We will start with the referees. So Professor Amos Fiat, maybe you can start asking your questions, please.
Yes, hello. Thank you for the presentation. I wanted to ask about the speed up you get when the number of rounds you get when you do the parallel version. So I know it's in the chapter, but I thought maybe you have a presentation on that. I saw you had a simulation as well.
Yes, so the question refers to the only thing I have on my slides is this small animation. So what happens when all the schools propose at the same time? And so the speed up I get from this is really at the beginning. At the beginning, all the schools propose at the same time. And so all the first proposals are really quick. But it takes a lot of time just for the few remaining people, like to match the last person. If there is n students, it takes roughly n steps to match the last student. So the speed up you get really depends on the number of people in the market. So if there is like 900 students and 1,000 schools, it's going to be very quick. The number of rounds will be logarithmic. But if you have exactly 1,000 students and 1,000 schools, because we want to match the last student and the last constant number of students are to match, this will take a linear time. So there is a gap between logarithmic and linear in this. Does it answer your question?
Yes, so I mean, if you were to run the thing serially, then the total number of proposals would be the same, right? Well, if I want to count a parallel round as consisting of many proposals, then I wanted to count the total number of proposals, and then how would these numbers compare? So there's two ways of counting, like number of rounds and the total number of proposals.
So the rounds. So each school sends proposals, but once a school found a student, it does not send proposal anymore. And so we have a lot of proposals sent on the first days, a very little number of proposals sent on the last days. And so the total I agree that the total number of proposals sent is the same if you use the sequential version or the parallel version. It's just the repartition of when the proposals are sent. And so if you can send a lot of proposals at the same time, that will speed up the process. But the fact that with a balanced market, with as many students as schools, the fact that it takes time comes from the fact that you need to match those few remaining students. And when there is only a few students who did not receive anything, there is a few number of schools that are still sending proposals, and this takes a lot of time.
So I guess the one measure by which the parallel version would be better is that in a short period of time, those that have left the game are happy. They don't have to worry anymore, right? There's a sense in which less people are anxious. I mean, admittedly, people could later have the choices change, but is there some measure by which you could say that somebody is, what would be if you wanted to argue in favor of parallel proposals, what would be the key argument?
So one way I think to answer your question is, okay, if, for example, yes.
Can you repeat the question before answering it?
Okay, I think I understood the question from Amos, which was how do you, so at some point during the execution of this process, students are going to change assignments when new proposals arrive. And he's asking about a measure of how much does this changes over time. And if it already converged after 100 rounds, why bothering for the last 1,000 if we only change a small portion of the stable matching? Is it what you asked about?
I was asking for a measure of stability over time. That would be a good way of phrasing it, yeah.
Yes, so there is several ways to quantify this, none of which I really know how to analyze and give analytic bounds. First one would be how many people already have their final assignment when I truncate the execution after a fixed number of rounds. So if I stop the algorithm, it's not converged, but that's okay. Let's look at the number of people who does not yet have their match. So that's one way of measuring it. And another way would be we also stop the process after some time, and now we look to how much unstable this matching is. And by counting blocking pairs, we said that a stable matching is a matching which has no blocking pairs, but maybe if we stop not too early, we only have a few blocking pairs. So this might be a harder question. I need to think about it. For the first one, I can say that, so the first one was if I truncate the execution after like n/2 rounds, for example, already a lot of proposals have been sent, only a linear number remain out of roughly n log n if I do the analysis. So I think if you stop the process after half of the round, only 1/log n fraction of people do not get their final assignments, but I need to check.
Thank you.
Okay, so next is Professor Tertieux. Please, Olivier, go on.
Thank you. So very short about Simon. So we met in Berkeley, I think, just pre-COVID time. And then we regularly talked together. So it was a pleasure to have you around these last years. And I'm an economist. I'm not a scientist. And you attended this reading group with us and presented several times. It was very nice for us to learn about what you were doing. I really enjoyed this learning from you. And also the PhD, I read it, and I was very impressed by the results, not only the results, but also the proof techniques, as I said in my report, and learned also many things. I think it's a good, I mean, first it's very clear, you know, the PhD thesis is extremely clear. The first chapters are very nice for a broad audience. And also, you know, one of the value for me was to learn about, you know, very simple, smart ideas on the proofs. Like what you presented was, you know, the first chapter, for instance, was very clear. It's a nice illustration of the type of new ideas that's in this thesis. You know, how you mix Peter's formula, inclusion exclusion principle, and the lattice structure is very nice. And you know, when you read the proof, it's very simple, but you know, you need to come up with the ideas. So this is nice. So I enjoyed it very much. And again, I think it gives ideas for even, you know, to go beyond what you put, and for people like me to think about how to handle some of the problems that I can think of. So, so this being said, I wanted to make a couple of comments, which are going to be essentially what's in the report. The first thing is I was interested in, we already talked about this, I think, in the past. I'm interested not only about core convergence, but also under what conditions we have large cores. There are some papers that actually empirically show that we do have large cores, meaning that, you know, Gale-Shapley student proposing and Gale-Shapley University of College proposing are going to be different. One of the contexts where it's true, and we were discussing this at lunch actually, is a context where agents, let's think about teachers, something I worked on students, have some kind of default schools to which they're allowed to, you know, they have the option to go there. And the way it's handled in practice is that those agents, let's say teachers, have a high priority for those schools. And it's typically the case where when you run schools proposing, the outcome is going to be very different from student proposing. And it's an environment where you intuitively, given that the school ranks one agent first, then conditional on this, the other schools are not going to rank it first for sure. So there is this kind of negative correlation going on here. I think it's interesting to think about how this type of distribution is going to, you know, expand the core, or to have a large core here. So it's related to some of what you have, and you know, the thesis is very rich. I may have missed. I'm sure you discussed many of these aspects, in particular in simulations. I was interested in particular in results like theorem 4.1 that you actually proved, mentioned, which is about you know, the expected rank of a given agent, the difference in terms of expected rank for a given agent between you know, two extreme points in the core. So student proposing, or men proposing, or women proposing, you provide in theorem a bound, not a bound, but I would be interested in knowing when actually this difference can be large. I don't know if you have any ideas on how it connects to the type of distribution I was mentioning before. So I know it's a bit going away from what you did, but at least I was interested in, this is one direction I would find interesting to dig into after this type of work. So this is my first question. So I get all right.
Should I try and answer something? Okay, what I understood from your question, thank you, is that sometimes, because of how the procedure is designed, there's this idea of having a safety, a choice, like a school where you can, it's some kind of outside option. And the school in which you're going to propose, or the school you prefer to this outside option, they're going to, you prefer the schools to the outside option. But those schools are outside options for other people that are going to be ranked very high for this. And so you said that there is like negative correlations between the preferences of students and of teachers and schools, because the schools I want to go in, it's a school that for which I don't have priority, and it's like this negative correlations.
I was thinking across schools, like conditional on a school ranking someone on top of a ranking. Conditional on this, the other schools don't rank this category on top.
But when this person ranked first, is it because this person is already coming from this school, or is it for some other external reasons? And so in chapter, let me try to find the. Sorry. So in chapter 5, I look at the effect of correlations on the number of stable pairs, which is a weaker notion than the convergence, the core, the fact there is a single stable matching. And I think, so we show that when you have positive correlations, it decreases, it shrinks the size of the core. So I don't have a model to have negative correlations, but in simulations, I tried some things, and indeed the number of stable matching increase when you add some negative correlations between the preferences of two sides.
Thanks. Just a second point. So you talk a lot about in chapters 4, 5, 6. Your motivation is really about incentives. So you're trying to relate small core to incentives. As I said in the report, there are some cases or some asymptotics where even though the expected number of stable partners is vanishing as the market grows, you may still have incentives to lie. So these are for other asymptotics. So what I would have liked is to see more formal elements here on maybe this is maybe you can just explain me what you have in mind in terms of incentives, and beyond this, you know, chapter one of the chapter, maybe chapter 5, is about comparing, you know, counting the number of stable pairs, right? And is there any value of doing this in terms of incentives? You know, if you move to so small core, in, you know, what you say small core, meaning, you know, the number of stable partners, when it vanishes, it's connected to incentives. What about the other notions, like the number of stable pairs? Is there any way to relate this to incentives? So this, even the chapter 4, 5, 6 are really about incentives. I wanted to know more about this. Beyond this, I have a question in my report, which is just this counting the number of stable pairs. Is it is the fact that it's different from counting the number of stable partners is something that holds true even if you have unbalanced markets? So this was something I was wondering about. And my last question, maybe I can ask it and then you answer the two. My last question is about Parcoursup. I really like the chapter 9. I was happy to read about this. You know, this question I think is really important. How quickly is this algorithm being converged? I was curious about what, the first time I thought about this. You know, this sequential version of Gale-Chaplet. How quickly should it converge? I was trying to think about this sequential version together with correlation in the university preferences of universities may make the process slow or slower than what it would be if we had just random you know, uniformly random draws of preferences of universities. In a sense, Parcoursup is about both introducing a sequential version of Gale-Chaplet plus having this correlation in the preferences. And I was wondering, I mean, reading your thesis, there was no, I mean, you were saying that it's kind of hard to handle the case with popularity, and I was reading just beyond the, you know, the math. What's your intuition? My intuition first was that, you know, if you have correlation, then the process should be slower, just because the authors are going to concentrate on a small number of students, and you know, as opposed to the case where you have uniform IID draws, where the authors will be spread over all students. So intuitively, it should be slower, but wasn't. So I didn't know what chapter 9 was saying about this, and maybe you can just provide some answers. Thank you.
Okay. I can try to answer the two questions.
Can you repeat the question?
Okay. Questions. First questions was in chapter 5, we count the number of stable pairs. How does it relate to incentive compatibility and the fact that people cannot manipulate and lie to get something better? So in Parcoursup, for example, we have the schools proposing to the students. And what are multiple stable partners? If I am a student and I receive something, a second stable partner for me would be rejecting the school that I already have for this school to propose to someone else, and this person accepting this new choice, and me getting the school that this other person had. And so that's manipulation is just me rejecting something to hope that it creates a cycle and goes back to me. And if there is a lot of stable pairs, it means that doing this, I can do it multiple times. And maybe there is a way to say that when there is a lot of stable pairs, the probability of this cycle going back to me is going to be high. If there is very few stable pairs, it means that I really shouldn't try to manipulate the system this way. So maybe the total number of the number of stable partners someone has is a measure on how likely it is that this procedure, this cycle goes back to me when I reject something. So that was the first question. The second question was about the convergence speed of Parcoursup, for example, or for the procedure where the schools all propose at the same time. And you were asking what happens if preferences are correlated. That means that some students are much more popular because they have good grades and they receive a lot of offers the first day. I think there is a theoretical answer, which is that if you run this algorithm with correlated preferences and all the preferences look the same, someone who's ranked roughly last will have to wait for a lot of time to get a proposal. So that's that will take a lot of time. And as many, if there is 1,000 students and I'm ranked 1,000th by all the schools, then it will need 1,000 days to converge. But that's the theoretical answer and probably not the best answer, because in real markets, some additional things have been made in place so that such things will not happen. The first thing is that preferences are not complete. So because I only apply to 10 schools, schools in average receive only, each seats only receive 10 applicants. And so this long preference list I need to go through will not be that long because of this limited number of. And the second thing is that in Parcoursup, for example, one of the solutions they found to speed up the process is to allow the school to overbook and to send more proposals than seats they have. And so this is a way to go faster at the beginning. And so one way to answer your question would be to look at this bit different model where you have you can send more proposals than the number of seats that you have, and this would be a more realistic response for your question. But I
think it was not about Parcoursup per se, but just comparison between uniform IID draws and just correlation.
So the comparison is that if there is 900 students and 1,000 schools with unit capacity, uniform will take a logarithmic time and correlated will take a linear time. And when you have the same number of schools and students, both are linear. And so the regime in which it's different, it's when you have fewer students than schools. And you see really a big difference between the two.
Okay, thank you. So now we'll hear questions from the examiners, and we'll start with Professor Feldman.
Hi. Thank you very much for the very nice presentation. Beautiful pictures too. I wanted to ask if so you didn't talk about it in this talk, but it was mentioned in the questions. And I wonder if you can clarify what is the main result in chapter 5 for the small number of stable pairs?
Yes, so number of stable pairs, it's counting over all the stable matchings. A stable pair is a pair of one student, one school, which are matched together in one stable matching. And to count this, in some model that I'm going to describe, it's going to be at most n log n, where n is the number of students and also the number of schools. And so the main result of chapter 5 would be if preferences of students and schools are positively correlated, which relates to what Olivier asked before, then the total number of stable pairs is at most n log n. And so this result was already known from Knut, Motwani, and Pitel when preferences are completely uncorrelated. And the main result is that when you add positive correlations, it just decreases.
So just to understand that so a trivial bound on the number of stable pairs would be n squared.
Yes.
Okay, so you're saying if it's so, in a sense, you are extending the previous result for independent preferences that showed an upper bound of n log n to positive correlation.
Yes, exactly.
And then intuition should tell us that if we have negative correlation, then we can go all the way to n squared.
Yes, so the worst deterministic example we have is, so without random models, there are some examples where you have n squared stable pairs, and it's just my first choice, I would be ranked last. So that's a negative correlation. And each person's first choice is ranked last. Each person's second choice is ranked second to last, etc. You have some kind of symmetry. And with this kind of, you can build an example with n squared stable pairs. But now what we can try and consider random models where you have these negative correlations and maybe try to count number of stable pairs. I need to think about what kind of model we can design.
And I see that in this slide, you put chapters 4, 5, and 6 under the question, who can manipulate?
Yes.
So can you explain how what you said now is related to manipulability?
Yes, so chapter 4 and 6 are clearly about incentives. Are people going to lie or not when reporting their preferences?
Yes.
Chapter 5, it's a bit more sketchy, and that's, but it is a measure of how far we are from the fact that there is a unique stable matching. When there is a unique stable matching, it's incentive compatible. No one can manipulate. And so this is what I meant by a weak core convergence. Like you have a weaker notion of not having a lot of stable matchings. This could be, we can try to argue and say that, well, it's related to the probability of me being able to successfully manipulate, but I need to think more about this. And yeah, so the chapter 4 is about incentive compatibility. It's not possible to manipulate, or its incentives are reduced. Chapter 6 is about what are the incentives, because clearly when people have a limited number of applications, they need to be strategic. And chapter 5 is somehow related, but not directly.
Okay, thank you very much.
Okay, thank you. Professor Thomas, Stéphane, you want to ask your questions?
Yes. Thank you. Hi, so thank you for your talk. This was really nice, as well as your manuscript. And this is nice for me also to be here after all these years that I could meet you. I've got a question in chapter 8. I'm trying to find a chapter which has not been asked already.
Yes.
So in this one, you ask for the rough equivalence of, say, a random stable matching, that is the average, and one which is determined by this theorem, which is, maybe you can recall me, 8.1. No.
Conjecture 8.1 is.
Yes, this existence of Synchron theorem. Yes.
Oh yes, okay.
So it seems that what you ask is the equivalence, rough equivalence between a fractional matching, in fact, because it's a barycenter of matching,
yes,
and a sort of fractional stable matching, which will be also. So do you have an idea of about the two structure could be the same, or put differently, can you tell more just about just the marginals, that is each probability of the pairs, but more on the structure? Why would they be the same?
So, so the question is about, so in chapter 8, I look at the probability of two agents being matched together. And this is aggregated over several stable matchings. So if school A and student one and school A are matched together, this could be in several stable matching. And so if you compute the average of all those stable matching, you get a fractional matching. So I know that there are some work about computing fractional stable matchings. And so this is interesting when you're allowed to output multiple stable matchings, because in some settings, for example, if you want to assign teachers or workers to timetables, or you're allowed to have several stable matchings because you can choose one each day of the week. And so having several stable matching is good because you can choose several of them. And the question now, if you have a fractional stable matching, is it a linear combination of multiple actually stable matchings? And so for this, I don't remember exactly what the results are, but there are some results where, so first there is several definitions of what fractional stable matching means. Some weaker, some stronger. For the strongest version, I think it's always the case that when you decompose it on and you compute a linear combination of matchings, all those matchings are going to be stable. For some weaker notion, a fractional matching will be the linear this fractional matching will be a linear combination of multiple stable matchings, but not all linear combination of representing this fractional matching are using stable matchings. So that does not really answer your question. You asked about the relationship between the fractional stable matching objects and the fractional matching objects.
I can ask. So first of all, you say that there's a little law of 1 over n. These are not exactly the. So in your question, in your conjecture.
Question. While you look, can we open the doors to air the room, maybe?
Yes. Yes. So in this theorem, I try to compute the fractional stable, a fractional matching, but because preferences are random, what I said about fractional stable matching before, it was for fixed preferences, but random matching. Now we have random preferences and random matching. And so this little o of n is about the random preferences, and the fractional matching is about random matchings. Okay. Yep.
Okay. Thank you. So I have a question also, but it's very selfish. This is only for my own interest, nothing for you. So I was very recently interested in what could be a correlated set of total orders on a set that is preferences. And I come up with the following definition. So you've got a set of total orders.
Okay.
And let's assume that one of these sets is identity.
Uh-huh.
And you say that the whole set is correlated if all other order are close to identity, and close is, if you see it as a permutation, it avoids a fixed pattern. You know what is a pattern in a permutation. So you fix your favorite pattern, and you say that a set of total order on a set is correlated if one of them being the identity, or the other one avoid the pattern. So they are all in some sense correlated.
Okay.
Have you ever thought of this kind of correlation among set? But does it follow from something which is known, or?
So I haven't thought about it. If the pattern is so I'm not quite sure what avoiding a pattern means in details, but if this could mean that, for example, student 1 to 10 are always ranked before student 10 to 20, that would be avoiding a pattern where you swap.
Yes.
And so if this occurs, or this kind of property, you can actually use this for the proof of chapter 4. But it will really depend probably on which pattern you choose, you want to avoid. A second thing that comes to mind is that there is other types of distribution, not using popularities, where you you would probably measure the number of violated pattern between this identity and this other matching, and you draw the other matching with a probability which is decreasing in the number of pattern that you do not respect. And so this might be related to Mallow's model, where you draw a permutation with a probability which is exponentially decreasing in the distance, which is the number of swaps between the two permutations. And so maybe there is some definition that could be made like this.
Okay, thank you.
Okay, thank you. So before we give the floor to the advisors, I will ask very brief questions. Thank you for this presentation and this manuscript. I enjoyed reading it a lot. It's extremely pedagogical. It's really a pleasure to read. I'm not a specialist of those topics. I know a little bit of matching. We were in contact together because of the game theory part, namely the games with incomplete information. So very small questions or remarks or opening to connections that I found while reading your thesis. One, in social choice or aggregation of preference or voting, you also have impossibility theorems between incentive compatibility and some various form of efficiency. There are some methods worked there where they say, okay, we know from whatever impossibility result that we cannot achieve incentive compatibility, but we look for methods that would minimize manipulability, that would be the less manipulable among some class of methods. So I was wondering whether your approach to this manipulability and those probabilistic methods would open up to having methods, algorithms, whatever, that would in some sense be the less manipulable that one can think of. That would be my first question. And the second one is about the game with incomplete information. Mm-hmm. So I noticed that the game is symmetric in the sense that from the perspective of one player, if you permute the other players, it does not change anything. Mm-hmm. So these games are somehow what I would call anonymous games. They have some anonymity property. Mm-hmm. So I wonder whether there would be a sense in going to the limit as the number of players tends to infinity, and whether there would be some limit game with a continuum of players, because maybe if we are dealing with large population, the influence of one person maybe becomes negligible. That's second question. And the last question, which is related to that, is whether in those games you mentioned in your manuscript multiplicity of equilibria. I wonder whether some form of correlation, but in a sense of correlated equilibria, that is of some central authority sending some correlated information to the players before they're choosing their strategies would improve welfare as opposed to Nash equilibria in behavior strategies as you consider.
Okay. So the first question was about social choice, aggregation of preferences, and if you're not able to have something completely incentive compatible, try the best and find the best procedure which is as close as incentive compatible as possible. So I would say that in algorithmic game theory, there is two parts: the design part where you come up with a mechanism, and then the analysis where you try to see if it's incentive compatible or not. And there is like a going back and forth between those two. And here I only focused in analysis. I never designed deferred acceptance algorithm. Like those were given by Gale and Shapley. And so most of my thesis would be more analyzing what happens for one procedure, for example, aggregation of when the input is not worst case, but is random. And so maybe there is something to be said here, like choosing the best procedure under some realistic conditions. So that would be one answer. Your second question was about this idea of in the game that we had. Let me find the slide with it. The fact that here I have a Bayesian game with a fixed number of students, and now I could, and this game is anonymous because there is a symmetry. All the students draw their type from the same distribution. And what happens if the number of students grows to infinity? Can we say something on at the limit? I looked at it, and it's possible to say some things, but they might have some strange behavior at the limit. So there is this paper by Azevedo and Leshno, which defines a model of stable matchings where you have a continuous set of students and a fixed number of schools. And so you can look at the limit of this Bayesian game and say it's going to goes exactly as in this paper. The problem is when you have multiple stable matchings. So if there is multiple stable matchings, the limit between having multiple stable matchings or not can be very thin, and at the limit it will be complicated. Like, let me explain. If there is more students than school, we know that the stable matching is in favor of the school, and if we have more school than students, it's in favor of students. And if it's in the middle, it's a very thin line. And when you try to come up with a game where you can have multiple stable matching, so if you are exactly at this limit, and you try to increase the number of students, and then the limit will not be very well defined, or I've not been able to have a very nice definition of the limit because and it's too technical. I would have to think more about it. But one very good thing which happens when you increase the number of students is that you can use the law of large number to know the other people. Because in this game, what I don't know is that, for example, I know that there is 3 students. They have grades between 0 and 10 uniformly. But if I knew that there were 10,000 students, I could say that there is exactly 100 students between 0 and 1, or 0 and 0.1 anyway. So that would be a way to use this information. And your third question was about correlated equilibria. That's a good question. We did not look at correlated equilibria for this game, mainly because we focused on examples of games where you both have you have a unique stable matching, which gives you a lot of good properties, such as sometimes even a unique equilibria. And so I don't really know what it would mean in terms of correlated equilibria. I need to think more about it, but yep.
Okay, thank you. So then we'll hear the advisors. Hugo, can you start?
Okay, thank you. First of all, I want to say a forward before asking a question. But it was a great joy to go alongside Claire and you all along your PhD. You really are a perfect PhD student, taking a lot of initiatives, a great scientific culture, always many ideas, leading the projects. It was really great. So thank you for these 3 years. I will ask a question, even though we have already discussed many questions, but you mentioned during your talk that you were partly motivated by practical applications of stable matchings. So my question is, among the open questions, open technical questions, which are still open about random matchings, what would be the one whose solving would have the most impact in practice for, I don't know, better design of matchings for Parcoursup or any other application like that?
Thank you, Hugo. That was so. The question is what kind of open question I would want to solve to have the most impact, and I think the answer is the bottom 2 chapters, chapter 6 and 9, because the first 4 chapters, the chapters 4, 7, 5, 8 are more about the outcome of student and school deferred acceptance, but those are problems that those are because student and school deferred acceptance have been around for a long time. We know we have some empirical results on this, and here I've been focusing on theoretical results, but those are theoretical results trying to explain some things that we know empirically. So I would not change much by proving some even better theorem. It will give theoretical understanding of it, but it will not be some new surprising result. For the chapter 6 and 9, solving those questions would maybe be even more important, because for example, in Parcoursup, when students have to choose which school they have to apply to. So yesterday I looked online and I typed strategy Parcoursup in Google to see what I was going to obtain. And there is a lot of articles from Le Point and L'Étudiant, etc., explaining that students should apply to the school they want, but also some safety school, but also some school that are. And there is a lot of things to be done here and to be understood. And the second thing would be chapter 9 with the convergence speed of deferred acceptance. It really it is important for the application in Parcoursup, for example, because you want this to converge fast, and having like a theoretical understanding of when it converges fast and when it does not could be a way to make sure that we never end up somewhere it does not converge. Or yeah, I would say that's the 2 chapters that could have the most impact.
Okay, thank you.
Thank you. So, the advisor, Claire.
Hello. Let me, in my turn, thank you for doing your PhD with us, Hugo and myself. I agree with Hugo that it's been a great pleasure to work with you and to see all the things you studied during these little over 3 years. Let me mention that in addition to his PhD work, during his PhD, Simon was also a lead participant in some work we did on modeling COVID-19 propagation in a social network, in a contact graph, and analyzing some mitigation strategies, a paper that was published in a biology journal. So he also did some significant work in some completely different area during his PhD. Okay, so thank you for everything. Let me just ask one question, even though I've had plenty of months and years to ask you questions. So the various things that you study, manipulability, strategy, number of stable matchings, convergence speed, etc. What is the effect on those parameters of the size of the schools, the capacity, when you have applications with schools and students?
So that's a great question. So for most of the results that I talked about, there is a generalization with capacities. So chapter 4, 5, 7, we can generalize and have some results on what the outcome of student and school year are going to be, because we can model a school with a big capacity, like several small schools having the same preference list, and so because they have the same preference list, it's the preferences are correlated, and it falls nicely in our hypothesis that preferences are correlated because that's the same school and they have the same preference. So that's good when we use those hypotheses that are strongly correlated. The problem with manipulability when you have capacities is that you don't only have to look at one person manipulating, because if you duplicate a school, now it's going to be like a collaboration, like a group of schools working together to manipulate and get something better. And so this is a stronger notion. And there are some papers. So in the literature of matching under random preferences and showing that there is a unique stable matching, the first paper that I know was the paper of Imorlika and Madian, who showed that when the preference lists are small, you have a unique stable matching. And there is this extension paper from Kojima and Patak, which looks at the same problem, but when you have schools that have capacity and can manipulate as a group. And they show that the same conclusion, almost the same conclusion is true. So it's a bit more complicated to show, but there is hope that the results that we have here can be generalized. The last thing I should probably do is that we should probably say is that for this last chapter here with the convergence speed of deferred acceptance, having capacities makes a huge difference because one school you cannot really if you duplicate one school and they all have the same preference list, all the seats are not going to propose to the same student the first day. If you have one school with 10 seats, you're going to propose to 10 different students on the first day, and that's one way. That's where this could fail. And so we have been looking at it with some people from Jussieu and INS in a group de travail. Bruno, who was here in the room. And so we have some conjectures about what happens when we have capacities. That's a work in progress, and that's really interesting.
Thank you.